at limits. I know this section is called Intro to Limits, but this is actually a long document and probably a longer video. One of the longer ones for the semester. There's just so much to cover with what I guess we can consider the intro to limits. So let's just get straight into it. So limits are the backbone of understanding the connection of algebra and geometry and connecting that all to the calculus. And the big idea of what a limit is, hey, what is a certain function doing as we are approaching a specific value? So we look at the x's and we're like, all right, as the function is approaching, say, 2. So x equals 2. What is the function doing? Is it going off to infinity? Is it going to negative infinity? Is it going to a specific value? So that's basically the idea of what a limit is what is the y value doing of a function? So we have a couple different, I guess I'll say types of limits, but we have directional limits and we have a general limit because sometimes they might be different, and that'll be something we need to look at. So the right-hand limit, you will see it written like this. We have the limit as x approaches some value c, and then it'll have a little plus sign here, and that's what's telling us it's from the right direction. And then we'll have our function. Right, the left hand, we have the limit as x approaches c from the left of the function. So we have the left side with a negative sign. And then the general limit doesn't have any sign at all. And so what we need for the general limit is we need to look at both sides, because for the general limit to exist, the left and right has to be the same. And so I know I spoke out what happened as I was writing. I'm just going to write verbally what all those are saying. So I'm going to pause my screen so I can write all that, and it's going to look like it's just going to magically pop in for you. So just a second here. All right. If I could do audio effects, I would have done like a magic thing there, because I know it just popped up on your screen. So pause the screen if you need to write this down. And here's just like a visual of why limits might be important. So we've got this bridge here, right? So we're approaching it from the left side and the right side to like build it all together. So I might not, looking at it, I might not see where they're connecting in the middle, where there's that space, but I know where it's tending to because of the left and the right sides. You know, they're both coming to the same point. Okay. And here's just the formal limit existence theorem. So the limit as x approaches c for f of x exists if and only if the limit from the left is the same as the limit from the right, and it's equal to L, where L is a real number. Okay. Let's look at it from a graph. So I obviously have this graph, and I'm going to evaluate some of these things. So a, f of 2, that is just asking for the function value. So at 2, I have a whole at 1, but I have an actual function value of -1. F of -1, again, a function value. So here's -1, I have a whole here, but I have a defined point at 4. Now we're getting into some limits. So, all right, the limit as x approaches 4 from the left. So here's 4, right? I sometimes will draw a line here so I know what I'm looking at. From the left side, so I'm going to follow this. This is the left side. So as I'm approaching x value of 4, the y value is going to 3. I'm going to do the same thing for the next one. The limit as x approaches 2 from the right. So here's 2. This one we want from the right. So I see that there's a hole there at 1, but the function is approaching 1. So it won't be equal to 1, but as I'm getting closer and closer to 2 from the right side, I'm getting closer and closer to 1. So that's why the limit is 1. Oh, now we'll go from 2 from the left side. So this other side here. So I do have a closed point there, but doesn't matter. It's what is it approaching? So we are approaching -1. And now this next part, we want the general limit. So remember, the general limit, the left and the right have to be the same. The left and the right here are different. We have 1 versus -1. So the limit as x approaches 2 does not exist. All right, now we're going to look at -1. So -1 from the left, again, there's a hole there, but it's still approaching 2. And then from the right, same idea. We are approaching the hole. It's 2. And then the left-hand limit and the right-hand limit are the same, so we can say that the general limit is also 2. Let's look at -4. All right, so -4 from the left. I don't have anything over here telling me a function even exists on the left side. So, does not exist. But from the right side, it's okay. We are approaching 2. And the general limit, because one side doesn't exist, the general can't exist. All right, what about 5? The limit as x approaches 5. All right, looks like it's approaching -2 here. Could argue infinity, but it doesn't, like that arrow keeps going, right? So at that point here, it's at -2. And then 0, as x approaches 0, -1. We'd have to check the left and the right, but it's continuous right there. But from the left, it's -1. From the right, it's -1. So limit is -1. All right, there are 3 cases as to why like a limit might not exist. So the first case is that the different sided limits don't exist. So I'll say differing sided limits. So in this case, the limit as x approaches -1 from the right is +1, but the limit as x approaches -1 from the left, it's down here, that's -1. These are not the same. So the general limit, the limit as x approaches -1 for the function, does not exist. And another case is what's called oscillating behavior. So we have this function here, sine of 1 over x. We want the limit at x equals 0. So we can do the sided limits. Just to double check here, right? We could do the limit as x approaches 0 from the right for the function, and the limit as x approaches 0 from the left of the function. And it's hard to see here, but what's happening at 0 is it's going up and down, up and down, up and down. And so if I pick something from the right of 0, let's say I substitute in something like 0.01, right? That's close to 0 from the right side. We'd have sine of 1 over 0.01. And if I plug that in a calculator, I get -0.5063. It's a long decimal, it keeps going. Right, so we could say, sure, from the right side, the limit is that -0.5063. And then if I do it from the left side, so let's pick a number on the other side. So how about -0.01? So, okay, sine of 1 over -0.01. That gives me a +0.5063. So they're on opposite sides. All right. So the sided limits here don't exist. Sorry, the sided limits exist. They are not the same. So the general limit doesn't exist. But as it's getting closer and closer, it's like up and down, up and down, up and down. So it's switching basically at every point. All right, and then this third case, we're going to call unbounded behavior. So going off to the infinities. All right, so even though I'm going to look at the directional and say, hey, the limit as x approaches 2 from the right is infinity, and the limit as x approaches 2 from the left is infinity. I know you're going to want to say infinity and infinity are the same, but remember the limit existence theorem, L has to be a real number. Infinity is not a real number. So we cannot say that the limit exists here. Infinity is not a real number. Okay. There are different properties to limits, and they are listed here. I won't go through all of them. I believe you can pause this and read this. I'm just going to apply the properties to different examples. So we can split sum and difference ones up. We can split products up. If there's a number in front, we can pull it out in front, almost like it's a GCF. And yeah, let's like apply these rules. All right, so I have a sum. So I can split it up and say, hey, the limit as x approaches 3 from the right of f of x. And then I can add the limit as x approaches 3 from the right for g of x. And then I can find them. So 3 from the right is 6. I got to go to g of x. And I want 3, but from the right, which is 8. And then 6 plus 8 is 14. I have a difference here, so I can separate them with subtraction. But then both of these have a constant here that I can like pull out. So 3 times the limit as x approaches 5 for f of x minus 2 times the limit as x approaches 5 for g of x. So f of x, as it approaches 5, we got to check both left and right. Left is 2, right is 2, so the general is 2. So 3 times 2 is 6. Then we'll do it here for g. So 5. Left is 4, right is 4, so the general is 4. And so we have 2 times 4, which is 8. So then 6 minus 8 is negative 2. All right, we have a subtraction again. So limit as x approaches 5 from the left for f minus the limit as x approaches 5 from the left for g. So we did just do 5 in the one before. So 5 for f was 2, and 5 for g was 4. 2 minus 4 is negative 2. We have some division here. So I can separate it with division. And then I have a constant here, so I can pull that out. So 3 times the limit as x approaches negative 7 for f divided by the limit as x approaches negative 7 for g. So let's find out. So the limit is negative 7. Negative 7. All right, left and right is 5. And then negative 7, left and right is 3. I can multiply it out, or those 3's will cancel, and I'm just left with 5. All right, we have 4 times the multiplication of f and g. So I can do this. I can say, hey, 4 times the limit as x approaches 3 for f times 4 times the limit as x approaches 3 for g. Or I could pull 4 out and do that all at the end. I might as well go ahead and do that. All right, for 3. 3 left and right is 6. G, for 3, the left and the right are not the same, so that limit doesn't exist. So it doesn't matter what these would multiply out to be, because one part of it doesn't exist, so the whole thing can't exist. All right, this squaring, I can do the limit and square the limit. So -3 for f of x, and then square that. So -3 comes down here. Left and right is -6. So -6 squared is 36. All right, the square root I can pull out at the end and do it all at the end. So square root of, and I will move that multiplier out front as well. So we'll square root 8 times the limit as x approaches 4 for g of x. G of x, we want 4. Left and right is 5. So we get the square root of 40. And then we should simplify that. I could break that to 4 times 10. 4 is a perfect square, so 2 root 10. All right, adding. So the limit as x approaches -3 for f of x plus the limit as x approaches -3 for g of x. So f for -3. -3, left and right is -6. Now, -3 for g of x doesn't exist. So, doesn't exist. All right, as we're approaching 6. So, the limit as x approaches 6 for f of x divided by the limit as x approaches 6 for g of x. So, f, 6 looks like 0, and then 6 looks like 5, and 0 over 5 is 0. And we have a composition here, and we'll get more into composition at some point during this video, but this composition, as long as it's continuous, I can say, hey, I can find the function value of the inside limit. So the limit as x approaches -2 of g of x. So -2 for g of x looks to me like -3. So f of -3 is -6. All right, we're going to go from not a graph this time. We're going to go from already being given limits. So the limit as x approaches c for f is 3. For g, it's -2. And for h, it's 4. So we're just going to still apply the properties in a different way. So I can square root the whole thing. And that's going to be 3 times the limit for h. I'm just going to go ahead and substitute those numbers in. So 4. And then 2 times the limit for g, which was -2. So that's going to give me 12 plus 4, which is 16. And the square root of 16 is 4. All right, we have the limit for f, which is 3. And then times 5 times the limit for g, which was -2. So 15 times -2 is going to be -30. I'm going to square this. The limit as x approaches c of 7, it's just a constant, and so that's just itself. Minus the limit for g. G was -2. And then we'll square the whole thing. 7 minus -2 is 9. 9 squared is 81. All right, this one's a lot to break up here. So we'll do division. 2 times the limit for f, which was 3, plus 3 times the limit for h, which was 4, over limit for 4 minus limit for g. Ooh. So 2 times 3 is 6, and 12, 6 and 12 makes 18. And then 4 minus -2 is 6. And so final answer of 3. Okay, I have a multiplication, so I can do h, which was 4 times, and then I have 2 right here. I can do f of x, which is 3, and then 6. Limit as x approaches c of 6, that's just a constant. So 6. I don't know why I put a multiplication when that's adding. So 3 plus 6 is 9. 9 times 4 is 36. All right, so limit for f and then squared. So that's 3 and then squared. 4, that's a constant. So the limit will be the constant itself. And then minus g, which was negative 2. So 9 over 6, and we can reduce that to 3/2. All right, so limits of composite functions. So if the function is continuous, then we can say that this piece here, we can do the function value of the inside limit, and it'll give us a value. But what if it's not continuous, right? That's the big issue when we are not continuous. So if that's the case, we can apply some things. So we've got the limit as x approaches c of some function is a number. And if that's the same as the one from the right, then we can say that it is the general limit. I'm not a fan of the way I just said that. We have to look at what's happening. And I think the best way to do that, because I don't think it's necessarily always going to be the plus. I think this is meaning a directional one. So let's look. So we would normally look at doing the limit of the inside one first, right? So it's as x approaches 1. Well, we're not continuous here. So let me let u be that inside one. So the limit as x approaches 1 for f of x. So if I look at that, the limit is going to negative 2, right? And then the function is coming at it from above in both directions. So I'm going to put a plus here. From above. So if I go to do the outside limit, so the limit for f of this one, well, I just used that as u. So f of u, I need to turn things in terms of u. So I have my u defined here. That's my new bound here. So u approaches 2 from above, which is the same as 2 from the right. So, all right, let's look at the function again. Erase my drawings. I'm looking at, and I meant to say negative 2. So negative 2 from the right, that limit is 4. So this entire limit is 4. Let's do it again for another one. So I want to use u as the limit as x approaches 0 for the inside function. I know in this case, both cases so far, it's been f and f. We'll eventually get to one where it's like f and g. So, inside function. So as it approaches 0, I have 2 different directions. I got the left and the right. So, and it's approaching what, 3? From above and below. So I need to do 2 different limits because it's going from 2 different directions. So the limit as u approaches 3 from the right for that outside function, and I should say for u, f of u, and then the limit as u approaches 3 from the left. So let's check those. So here's 3. From the right, it's 1. From the left, it's 3. And these are not the same. So this whole limit here does not exist. All right. Let's look at some more. I should have given more space here for these U substitutions. This is another similar one with f of f, but U will be the limit as x approaches 1 for the inside function. So here's f. And as it approaches 1, we are going -3 from above. So we'll do the limit as u approaches -3 for f of u. So -3. And we want from above, so that's going to be 2. Oh, and I forgot to put my low plus. All right, here's where we have two different functions. So u is the limit of that inside. So the limit as x approaches 2 for g of x. So here's g of x, here's 2. And we have two different directions here, right? I've got, it's, oh, no. Yeah, hang on. Sorry. As x approaches 2, we've got to use 2 u's because these limits are different. So, do I want to use 2 different u's? Let's use u and v. So 2 from the left is 4, and then it's from below. So if I do the limit as u approaches 4 from the left for h, we get 4 from the left would be 1. I'm going to use v. v is going to be the limit as x approaches 2 from the right of g of x, which is 1, and again, it's from below. So then the limit as v approaches 1 from the left for h. Here's h, and we want 1 from the left, which is 4. And I should just scratch this whole thing because I'm messing up. Because one, that should be u. And this right here, I'm sure you've already caught it by the time I have. This should be 3. So this would be 3 from below. So 3 from the left is 4. And these two limits are the same. So this entire limit is 4. All right. Now that I've corrected all my mistakes, hopefully you've corrected it before or you were raising questions before. Oh my gosh. I need to be so much better with slowing down and paying attention because that should have been V. I changed it to a V notation. All right. Let's try it again and I'm going to go a little slower. So I need to do the inside. So I'm going to do u is the limit as x approaches -1 for h of x. Erase all my previous drawings. So 1 for h of x, that limit is 4. Oh my goodness, this is actually crazy. That would be correct for 1. My number here is -1. So let's do this again. -1. The limit is -4, and from both directions, it's coming from above. So 4 from above. So I don't have to separate it into two because that limit was the same from the left and the right. The function was coming from above. So as u approaches 4 from the right, for g of u. So here's g. We're approaching 4 from the right, which is going to give us, oh my goodness. I hope you are as entertained. Okay, I'm redoing this whole thing. I can't. And I'm 30 minutes into it, so I'm not going to redo the first 30 minutes just to perfect this one. So, whoop, scratch that. Try again. U is going to be the inside, so the limit as x approaches -1 for the inside function. So h of x, -1. The limit from the left and the right is -4, and both functions directions are coming from above. So I only have to do one u substitution. So the limit as u approaches -4 from the right for that outside function g. So here's g, -4 from the right is -3. So that limit is -3. All right, I'm going to redeem myself with doing these. All right, so u is going to be the limit of the inside. So the limit as x approaches -3 for g of x. So here's g of x. We're going to go to -3. And our limit is -4 from above. So -4 from above. So I can do my limit as u approaches -4 for now f, the outside function. So here's f. We're doing -4 from the right, and that's going to give me -1. All right, we'll do u as the limit as x approaches 2 for that inside function. So here's g, here's 2, left and right. We got 4 from below. So the limit as u approaches 4 from the left because of the function coming at it from below for f of u as 4 from the left is 3. All right, these next two ones here, we're going to approach this a little differently. So this says f of, and it gives me a totally different function. So I'm going to analyze that function. That function is a downward facing parabola, and that was shifted. It's going to look something like this, right? So we want to do, we could say that u is the limit as x approaches 2 from the right for that inside. Now we could do the like algebra for it, but let's look at the function. If I go 2 from the right, I can just find that function value. So 8 minus 2 squared, which is going to be 8 minus 4 to give 4. Right? And since we're looking at the directional side of it, we're only looking at from below. So when I go to do the outside limit, so the limit as u approaches 4 for f. So go into f. I'm going to look at 4 from the left, which is 3. And this next one, we have g of 2 plus f of x. So we can split that. We can say, hey, u is the limit as x approaches -4 from the right for 2, plus the limit as x approaches -4 from the right for f of x. So that's a constant, so it's going to stay the same. And then we want f of x. So here's f of x. We want -4 from the right, -4 from the right, which is going to be -1. So it's going to give me 1. So the limit as u approaches 1 for g of u G1, that's going to be 2. All right. So we've done it with graphs. We've done it with being given the limit of a function. Now we're going to do it with given the actual equation. So this is called doing it analytically. So we can do direct substitution, where we can directly substitute the value in for all the x values. That might give us a value, and if not, we can try some other methods. Maybe we can factor and simplify. Maybe we have to conjugate or rationalize. Or we might be able to use trig limits. So we can do a direct substitution in for a few of these. So whenever you do a direct substitution, you can drop off the limit notation because we are substituting in the value. So let's see, 4 times 3 is 12 minus 10 plus 4. So it's going to give me 6. You can do a direct substitution here too. So 2q plus 1 over 2 plus 1. 8 plus 1 is 9. And 3. So 3. Substitute in e. So natural log of e over 3 times e. Natural log of e is 1. So 1 over 3e. Substitute in here. So we have the cubed root of 4 plus 4, which is the cubed root of 8, which is 2. All right, we got sine of 2 times pi over 6, which will give us sine of pi over 3. And sine of pi over 3 is root 3 over 2. We can sub in 5, so log base 3 of 5 plus 4 gives log base 3 of 9. And log functions, remember the answer is the exponent, so 3 to what power gives 9? So 2. All right, now what if the direct substitution gives us something weird? So I'm going to do a direct substitution here. 4 squared is 16 plus 4 is 20 minus 6 is 14. And then 4 squared is 16. 4 times 6 is 24 plus 8. And that gives me 0. So that's an undefined number right there, right? We can't have 0 in the denominator of a fraction. So let's try and factor and cancel out. So from this point, because I'm going to factor, I'm not substituting in a value anymore, so I need to keep that limit notation. So the limit as x approaches 4. And then I'll try and factor the numerator and denominator. So let's see, probably 3 and 2. We want a positive 1, so plus 3 minus 2. And then in the bottom, 2 numbers that multiply to 8 add to -6, so -4, -2. So, all right, I can cancel that out. I'm still not evaluating yet, so I need that limit notation. And we have x plus 3 over x minus 4. And now if I do a direct substitution, 4 plus 3 over 4 minus 4 now gives me 7 over 0. And when you've done all the simplifying that you can and you still get a number over 0, we actually say that this doesn't exist, because this is going to create a vertical asymptote. think back to rational functions. Having a 0 in the denominator creates a vertical asymptote. So it's that unbounded behavior, right? So the general limit will not exist. All right, well, using this, it's the same function. So I'm just going to go ahead and write the simplified part, right? So the limit as x approaches 4, we're going to do left and right, of x plus 3 over 4, oh, not 4, x minus 4. I'm going to write it here as well. So the limit as x approaches 4 for x plus 3 over x minus 4. So if we're going from a perspective of, we don't have the graph, but we have the equation, and we want to find the sided limits. So we can plug in values to the left and the right that are very close. So maybe I want to use, let's see, 4 from the right, maybe 4.1. I'm going to plug in 4.1 and see what happens. So 4.1, oops, plus 3 over 4.1 minus 4. I'm just looking at, because I know it's a vertical asymptote, I'm just looking for the sign. You know, I just want to know, am I going to positive infinity or am I going to negative infinity? So 4.1 plus 3, doesn't matter what the number is, it's a positive. And then in the denominator, 4.1 minus 4, also positive. And a positive over a positive is going to give a positive. So this is going to positive infinity. And then we can think, rational function analyzing wise, the x minus 4 factor has a multiplicity that's odd because there's only one of them. So approaching that vertical asymptote, it's going to have to approach it at different sides. So if it was even multiplicity, it would approach infinity on the same side. But because it's odd, it's going to go opposite. So I'm going to go ahead and write a little note that I think this is going to be negative infinity. But if I don't remember that fact, I can do the same thing and say, hey, let's plug in a number to the left of 4. How about 3.9? So 3.9 plus 3 over 3.9 minus 4. Again, just looking at signs, 3.9 plus 3 is positive. 3.9 minus 4 is negative. So in the end, this is negative, which means we're going to be going to negative infinity. It's cool. All right, got some piecewise functions here. So we want to find the limit. So remember, for the general limit to exist, the left and the right have to be the same. So I want to find the limit as x approaches 1 from the left. And I want to find the limit as x approaches 1 from the right. This piecewise will tell us the directions. So greater than 1, it's going to be that right side. So I want the limit as x approaches 1 from the right of x cubed plus 1, which means from the left it'll be the other one. So limit as x approaches 1 from the left for x plus 1. Okay, so these are polynomial functions, and they are continuous. So we will have, we can just do direct substitution. So plugging in 1. 1 plus 1 is 2. And then plugging in 1. 1 cubed is 1. 1 plus 1 is 2. These are the same, so the limit is 2. And we're going to do the same thing here. So the limit as x approaches 2 from the right is going to come from this bottom equation here. And the limit as x approaches 2 from the left is going to be that top equation. So let's do that direct substitution. So negative 2 squared plus 2 times 2 minus 1, negative 4 plus 4 minus 1. And I definitely meant for that to not be what I wrote. That should be 4. So that'll make that 8. So then 4 minus 1 is 3. Let's try it here. So 2 squared minus 4 times 2 plus 7. It's going to give me 4 minus 8 plus 7, which is negative 4 plus 7, which is 3. These are the same, so that limit is 3. Okay, we have some complex fractions in here. So what I like to do with these is rewrite these so that they are in one fraction. So I'm going to look at just this bottom piece here. So 1/4 plus 1 over x minus 4. I want to get that into one fraction. So I need a common denominator, and the easiest way to get the common denominator is to just multiply the denominators together. So this first fraction part is missing an x minus 4, so I'm going to multiply both numerator and denominator by x minus 4. And this second one is missing 4. So I know my common denominator is now 4 times x minus 4. And then the numerator, x minus 4 times 1 is x minus 4. And 4 times 1 is 4. If I simplify this, those 4's are going to cancel out. So I'm left with x over 4 times x minus 4. Now remember, that's just the denominator. So I have the limit as x goes to 0 of x over 4 times x minus 4. Now what I do from here is I was always taught that we can make that top one a fraction, right? And then I was always taught a fraction over a fraction is going to be the same as if we did big C over little c. Because what's happening is you're keeping the first fraction. You're multiplying by the reciprocal. You're changing to multiplication and then the reciprocal. So 4x minus 4 over x, right? And look at that. Big C was x times 4 and then x minus 4. And little c was the 1 times x. So that's why I do big C over little c. So I'm left with, and we can see those x's are going to cancel out. The limit as x goes to 0 for 4 times x minus 4. And it'd be over 1, but I'll just leave it. Now I can do a direct substitution of plugging in 0. And I get 4 times negative 4 to give me negative 16. And then I can apply that same idea over here. So let's simplify that numerator. I know my common denominator is going to be if I multiply them both. So 2 times 2 plus x. This first fraction is missing a factor of 2. And then this second one is missing a factor of 2 plus x. But I'm subtracting it. So I need to subtract 2 and subtract x. So simplifying this out will leave me with negative x over 2 times 2 plus x. And again, that is just the numerator. Negative x over 2 times 2 plus x all over x. So I'm going to apply the same thing and make this one a fraction. And then I'm going to do big C over little c. So the limit as x goes to 0 of big C, so negative x, over 2x times x plus 2 or 2 plus x. Cancel out the x's, so the limit as x goes to 0 is negative 1 over 2 times 2 plus x. Then I can substitute in 0, so negative 1 over 2 and 2 plus 0. And that's going to leave me with negative 1/4. Okay. The conjugate and rationalizing, so that's if we have square roots involved. If I do my direct substitution, it's going to give me a indeterminate form, so I need to do some algebra. And the conjugate, what we want is to be able to cancel out a factor. Because right now, doing that direct substitution is leaving me with a 0 in the denominator. So what I'm thinking is I might be able to cancel out a factor of x plus 1. So I need to multiply by the conjugate. So instead of the square root x plus 2 minus 1, conjugate is square root x plus 2 plus 1, because that's the result of like a difference of squares. So if I multiply both like this, so the limit as x goes to negative 1. If I multiply square root by square root, it's the same. Gets rid of the square root. If I multiply the square root of x plus 2 times 1, but then I also multiply -1 times that same square root, that middle term is going to cancel out, and I'm left with just that outer term, which is going to be -1. Now in the denominator, I'm not going to try and FOIL that out or multiply that out, because watch the magic that's about to happen. I can combine some like terms, and I get x plus 1 over x plus 1 times x plus 2 plus 1. Those factors cancel out like I wanted them to. So the limit is x goes to -1 of 1 over the square root of x plus 2 plus 1. Now I can do a direct substitution and it should work. So 1 over. -1 plus 2 is 1. So square root of 1 is 1. 1 plus 1 is 2. So got a limit of 1/2. We're going to do the same thing over here. So I probably want a factor of x minus 5 to cancel out. So I'll multiply by the conjugate. 3 plus the square root of x plus 4. Numerator, I'm not going to distribute that out. I'm going to leave that as x minus 5 times 3 plus the square root of x plus 4. But in the bottom, I will multiply that out. 3 times 3 is 9. The middle terms will cancel out, but I'm left with minus x plus 4. So I have to distribute that negative, minus x minus 4. So I'd have negative x plus 5. Now that's not x minus 5, but if I factor out a negative here, and I'm just going to do it in a different color, then I'll have x minus 5, right? Then I can cancel those factors out. Oh my gosh, I've dropped my limit notation. Limit as x goes to 5. So now the numerator is just 3 plus the square root x plus 4. And then the bottom, I'm just left with a -1. Now I can do a direct substitution in. And I've got 3 plus 5 plus 4 is 9. And then -1. 3 plus 3 is 6 over -1 is -6. I guess I could have taken the negative out of the numerator, so I wasn't left with a denominator, but it's okay. All right, let's see if we can substitute in. So if I plug in 3, 15 plus 1 is 16 to the 2/3. 16 squared is 256, and then we want cubed root, and let's try and simplify. So I know that that's 16 and 16, and that's 4, 4, 4, and 4. Take it out in groups of 3, so that's 4 cubed root of 4. Let's see if I do a direct substitution in, I get a 0 in the denominator, so let's just go ahead and rationalize. So the limit as x goes to 3, the denominator will stay x minus 3 times the square root of x plus 1 plus 2. In the numerator, we will get rid of that square root. And then we have to do the back end, which would be -4, which in the end will simplify. I'm going to just write it in red as x minus 3 so we can cancel that out. So the limit as x approaches 3 for 1 over square root of x plus 1 plus 2. Then I can do a direct substitution. 3 plus 1 is 4. Square root of 4 is 2. 2 plus 2 is 4. So we have a limit of 1/4. All right, we got one last page here. So the limit as h goes to 0 for this entire function here. So let's just go ahead and distribute a lot of things out. So the limit as h goes to 0, let's multiply that out. So that's x squared plus 2xh plus h squared. And then minus 3x minus 3h minus x squared plus 3x all over h. We'll have some things that'll cancel. We got x squared and x squared, 3x and 3x. So I'm left with the limit as h approaches 0 of 2xh plus h squared minus 3h all over h. But notice each of these terms have an h in it, so I can factor out an h. So I'm left with the limit as h goes to 0 of 2x plus h minus 3. Then I can do a direct substitution of 0 and be left with 2x minus 3. And I lied, there's 2 pages left. Trig. Got some trig functions here. So use direct substitution to find the limit. All right, so cosine of 2 times pi over 3 over pi over 3. So let's see. Cosine of 2 pi over 3 is a negative 1/2 over pi over 3. I can apply that same. It's fraction over fraction, so big C over little c to give me negative 3 over 2 pi. All right, direct substitution. Let's see, we get 3 times sine of pi over 2, and then we can square that. Sine of pi over 2 is 1. 1 squared is 1, and 1 times 3 is 3. All right, well, maybe if I do a direct substitution in here, cosine of pi over 2 is 0. 0 squared is 0. And that leaves me with a denominator of 0. So let's try and do some trig substitutions in here to see what might be able to help us. So I'm going to make cosine squared. I'm going to use the Pythagorean identity. And I'm going to make this the limit as theta goes to pi over 2 of sine of theta minus 1. And I'm going to make this 1 minus sine squared. Okay, that's that Pythagorean identity. And then this is a difference of squares. So I'm going to factor that. So the limit, if we go to pi over 2 of sine minus 1, and then this is going to be 1 minus sine and 1 plus sine, right? So I can cancel out one of these factors if I were to take out a negative 1 on top, right? We're left with negative sine and then plus 1, which is the same as 1 minus sine. So I'm left with the limit as theta goes to pi over 2 of negative 1 over 1 plus sine of theta. Then I can do a direct substitution. And sine of pi over 2 is 1. So I get a final answer of negative 1/2. Okay, let's do some more trig here. Okay. Off the top of my head, I don't know what cotangent of pi over 2 is. So what if I rewrite cotangent? Because tangent is sine over cosine, right? Cotangent is the reverse. Cosine over sine. So I have the limit as we go to pi over 2 for 2 cosine times cosine over sine. Okay, I can go simplify just a tiny bit and say that's 2 cosine squared over sine. I think I can do a direct substitution from there, right? Pi over 2, cosine of pi over 2 is 0. 0 squared is 0. 0 times 2 is 0. Sine of pi over 2 is 1. So final answer of 0. All right, let's rewrite tangent as sine over cosine. So we have the limit as theta goes to pi over 4 of sine cosine over sine over cosine. I'm going to do my big C over little c because I'm going to make that top one a fraction. Big C, little c. To get sine cosine squared over sine. That can cancel out. So then pi over 4. I can do a direct substitution in now. Cosine of pi over 4 is the square root of 2 over 2. And then I can square that. So 2 over 4 to get 1/2. All right, and there's a typo in this one. This is not supposed to be cosine of theta. This is supposed to be cosecant theta. Because I can say that cosecant, isn't that 1 over sine? And then that can cancel. So I'm left with what? 1 over 3 theta, which is 1 over 3 pi. All right, we do have some special trig limits, okay? Yes. That you just kind of need to memorize and work with. So the limit as theta goes to 0 for sine of theta over theta is always going to be 1. And then for cosine, the limit as theta goes to 0 for 1 minus cosine of theta over theta is 0. We need to know how to manipulate some of these things to be able to use them. So like in this case here, I have sine of 5 theta over 2 theta. I need these two things to be the same, sine of theta over theta. So I need this bottom one to be some form of 5 theta. So what I can do is multiply both numerator and denominator by 5. And let's see what happens when I do that. So I got theta minus 0, as it goes to 0, sorry. That's going to be 15 sine of 5 theta over 10 theta. And then I think I can factor a number out so that instead of 10 theta, I'll do it in a different color, we actually have 2 times 5 theta, right? So then if it looks like that, the limit as theta goes to 0 for 15 sine of theta over 2 times, that's supposed to be a 5. This 15 over 2 is a multiplier. So pull it out, right? So 15 over 2 times the limit as theta goes to 0 for sine of 5 theta over 5 theta. This entire thing here, 5 theta over 5 theta, matches this. So that's just 1. So 15 over 2 times 1 is just 15 over 2. All right. So this one, we're going to split this up because I want 1 minus cosine over theta. And I have that here. I just had to split it. So I can do the limit as theta goes to 0 for 1 minus cosine of theta over theta, which we know goes to 0, plus the limit as theta goes to 0 for sine of 3 theta over theta. I want to use the trig limit, or the sine limit, right? Sine of theta over theta. So I need to multiply them both by 3 so that they match. So I get the limit as theta goes to 0 for 3 sine of 3 theta over 3 theta. 3 is that multiplier. So the limit as theta goes to 0 of sine of 3 theta over 3 theta. This goes to 1. So I've got 0 plus 3 times 1, which is just 3. All right, I told you that this intro to limits was a longer video because there's a lot that goes into just limits and trying to evaluate them. So if you have any questions, let me know.